July 7th, 1942. The airstrip at Henderson Field, Guadalcanal. An American pilot named James Grayson was about to take off in his F-6F Hellcat when his propeller simply shattered. Not from enemy fire, not from mechanical failure, from heat. Pure, relentless heat that had crystallized the metal until it fragmented like glass. He was only 300 feet in the air when it happened. The right engine seized. The propeller blades separated from the hub and tumbled through the jungle canopy like twisted fingers. He crashed into the palm trees, walked away with burns on his face and a concussion that wouldn't fade for weeks, and asked a question that nobody wanted to hear. Why does nobody know how to make a propeller that doesn't destroy itself in a tropical combat zone? 3 days later, he asked it again to a Navy engineer who just stared at him and said, "It doesn't work that way. We can't just make metal that doesn't fail." But someone could. And his obsession with understanding metal, his refusal to accept impossible, would eventually save more lives than any tactical maneuver during the war's most brutal campaign. This is the story they don't teach in military history. The story of Dr. Raymond Holbrook, a metallurgist with no fighter pilot experience, no combat training, and absolutely no business being involved in Pacific warfare. A man who wore glasses and kept careful notes in leather-bound journals. A man who talked about crystalline structures at parties where everyone else wanted to talk about strategy and heroics. This is how he changed everything. Stay until the end, because what happened next shocked generals, frustrated admirals, and proved that sometimes the most dangerous enemy isn't the one shooting at you. It's the one whispering in your ear that your metals are good enough. The Pacific War wasn't like Europe. It wasn't about calculated advances across known terrain with established supply lines and predictable logistics. The Pacific was chaos wrapped in humidity, served on islands that seemed designed specifically to break everything Americans brought there. And nothing, absolutely nothing, broke faster than aircraft. When the war began on December 7th, 1941, American aircraft were technically superior to what the Japanese were flying. The Hellcat, the Corsair, the Mustang, they were better engineered, better armed, better designed. They were engineered by men who had worked in California and Connecticut and Kansas. They were tested in dry air. They were designed for predictable conditions. They were not designed for what happened when you took them to the Solomon Islands, to Guadalcanal, to Bougainville, to places where the very air seemed to be trying to kill you. The temperature didn't just climb in the Pacific theater. It assaulted you. 95 degrees Fahrenheit in the shade at dawn. 103 by midday. And that wasn't the real problem. The humidity was the problem. 98% humidity that made you feel like you were breathing underwater. Add the salt spray from ocean operations, the rain that came in sheets during tropical storms, the perpetual moisture that condensed on every metal surface no matter what protective coating you applied, and you had an environment that attacked aircraft in ways the engineers had never calculated. The problem wasn't singular. The problem was that everything was failing at once, in ways that made no sense. The propellers that had spun reliably for thousands of hours in the continental United States began to develop micro-fractures, not visible fractures, not the kind you could see during a thorough pre-flight inspection. Invisible weakness that accumulated in the metal's crystalline structure like a debt-accruing interest. A propeller would operate perfectly for 50 hours, maybe 100 hours, maybe even 200 hours in some cases. Then, without warning, during a critical moment, a combat approach, a bombing run, a tight formation where you couldn't recover, the metal would lose its integrity and shatter. not fail gradually, not crease or bend or develop visible damage, shatter catastrophically, explosively, as if the metal suddenly remembered it wasn't supposed to hold together anymore. Pilots called it the sudden death phenomenon, and nobody could explain why it happened. Nobody could predict it. Nobody could prevent it. Engineers at the Naval Aviation Supply Center blamed manufacturing. "The tolerance standards aren't tight enough," they said. "We need tighter quality control." They demanded metallurgical analysis, X-ray inspections, flame testing. Pilot training programs blamed handling procedures. "You're revving the engines too high during takeoff," the flight instructors said. "You're putting too much stress on the propeller during combat maneuvers." Supply officers blamed improper storage. "The propellers aren't being kept in climate-controlled warehouses. Salt air is corroding them in transport." Not because of mechanical failure, not because of design flaws in the aircraft themselves, but because everyone was blaming something different, which meant nobody was actually understanding what was really happening. By mid-1942, American pilots in the Pacific were living with a terrifying calculus. Every mission might be the one where your propeller decided to betray you. Every takeoff was a gamble. You could be the best pilot in the squadron. You could have trained for 2 years. You could have survived 5 combat missions without a scratch, and on the 6th mission, your propeller would simply decide to come apart. The Hellcat could outmaneuver a Zero. Your training could help you overcome tactical challenges. But there was nothing you could do about metal that was systematically destroying itself from the inside. Working on a timetable nobody understood. The medics were overwhelmed. When a propeller failed at 5,000 feet during an attack run, there was no recovery sequence, no emergency procedures, no ejection moment. Just gravity and the sound of metal tearing itself apart, and then silence as the aircraft began to fall. Another pilot added to the casualty lists that nobody wanted to talk about, because the casualty lists weren't supposed to include pilots lost to their own equipment. That wasn't supposed to happen in a war about better tactics and better pilots and superior industrial capacity. The engineers at naval air stations from San Diego to Hawaii were working 16-hour days trying to find solutions. They tested protective coatings. They experimented with storage methods that kept propellers sealed in dry containers. They demanded better manufacturing standards and tighter tolerances. They consulted with aircraft designers and aeronautical specialists. Nothing worked because nobody understood the actual problem. The propeller wasn't failing. The metal was transforming. The crystalline structure was reorganizing itself, and tropical heat combined with humidity and salt spray was the catalyst. Every month brought new failures. Every month brought another report. Every squadron's paperwork included another line. Aircraft lost to mechanical causes. The tactical nightmare was that you couldn't predict it. You couldn't see it coming with your eyes. You couldn't hear it with your ears. A pilot could be the best in his unit, could have survived 20 combat missions with medals on his chest, and then on mission 21 he'd become a statistic. Not shot down, not killed by enemy action. Killed by something happening at a molecular level in a piece of brass and steel spinning at 2,400 revolutions per minute. The death toll climbed. By the summer of 1942, propeller failure was accounting for nearly 15% of non-combat aircraft losses. That was hundreds of pilots. Hundreds of families getting letters that said their sons had been lost in an accident, not realizing that the accident was something that could have been prevented if anyone understood why metal was changing its behavior under tropical conditions. By July of 1942, the problem seemed completely unsolvable. Except one person refused to accept that possibility. Dr. Raymond Holbrook was not a pilot. He had never flown a combat mission. He had never worn a military uniform or taken orders from anyone with authority. His only connection to the war effort was a civilian consulting contract with the Naval Materials Research Laboratory in Washington, D.C., a job that paid him $38 per week and gave him access to equipment and resources that most private researchers could never have hoped for. Before the war, he'd spent 15 years studying the crystalline structure of metals at a small private laboratory outside Pittsburgh, Pennsylvania. Most military officers had never heard of him. Most people didn't know what a metallurgist did, let alone why one would matter in a war about tactics and logistics and industrial production. But Holbrook had an unusual gift. He looked at metal the way a musician looks at a symphony score. Where others saw a finished product, he saw a story written in molecular structure, in the arrangement of atoms, in the way elements bonded together under different conditions. He understood that metal wasn't inert. It wasn't just a solid material that stayed the same forever. Metal was alive in its own way, constantly shifting, constantly reorganizing itself based on temperature and stress and composition and time. It had moods. It had weaknesses. It had secrets. When he first heard about the propeller failures in the Pacific, he was sitting in his laboratory in Washington on an August morning in 1942, reviewing reports that were supposed to remain classified. A colleague named Dr. Eleanor Vasquez, one of the few female engineers in the Naval Materials Division, had slipped him the files because she knew he was interested in material degradation in extreme conditions. The reports described the sudden death phenomenon, the inexplicable failures during flight, the complete lack of any visible defect in the propellers that had shattered. Something clicked in his mind instantly, like a key turning, like a combination lock opening. He immediately began asking questions that nobody else had thought to ask. What was the exact temperature during the failures? Not approximate, exact. What was the humidity level? Had anyone measured the salt deposit concentrations on failed propellers compared to successful ones? What was the precise composition of the brass alloy being used? Had anyone tested the same propeller materials in a humidity chamber that matched Pacific conditions? Had anyone examined the molecular structure of failed propellers versus functioning ones? The answers came back marked urgent. No, nobody had done those experiments. Everyone assumed the failures were random acts of mechanical fate. Everyone assumed the problem was random because they had no framework to think about it systematically. Nobody had tested the propeller material in conditions that actually matched the Pacific theater. Nobody had thought to recreate Guadalcanal in a laboratory. Holbrook understood something fundamental that the aircraft engineers and pilot training programs did not. The problem wasn't the design of the propeller. The problem wasn't the pilot's technique or the altitude at which they operated. The problem was that the brass alloy used in standard propellers undergoes a specific metallurgical transformation when exposed to precise combinations of temperature and humidity and salt. It's called stress corrosion cracking, though Holbrook would have described it differently. He would have said that the crystalline structure of the brass becomes unstable. The metal develops invisible microfractures that cascade through the material, like cracks in ice. These fractures accumulate over time, and eventually, at some unpredictable moment during operation, the entire structure suddenly gives way simultaneously, all at once. It wasn't a catastrophic failure point. It was a cascading molecular collapse. The metal was surrendering itself. Holbrook's insight was deceptively simple. Find a metal that doesn't transform under those specific conditions. Find an alloy that remains stable no matter how hot it gets, no matter how humid it becomes. no matter how much salt corrodes its surface and tries to disrupt its molecular bonds. Redesign the propeller to use that metal instead. The challenge was that nobody made such a metal. Not yet. Not in the quantities required for mass production. Not in forms that could be easily machined and forged into complex propeller shapes. He started with notebooks, 3 leather-bound journals that he filled with calculations in his cramped handwriting. He sketched out hypothetical alloys, combinations of metals that had never been tested together in this specific application. He thought about aluminum composites, about titanium compounds that were still mostly theoretical, about nickel-based alloys that were expensive and difficult to machine, but remained stable under extreme stress. He worked late into the evenings in his small laboratory, surrounded by testing equipment that hummed with purpose, with his hands cramped from documenting observations and his mind consumed by the puzzle like an obsession, like a disease that he didn't want to cure. His colleagues thought he was obsessed. Maybe he was. But his obsession came from something simpler than pure scientific curiosity. He'd read the casualty reports. He'd seen the names. He understood that pilots were dying not in combat, not from enemy action, but from something invisible. Something that could be solved by someone willing to actually understand the metal instead of just using it and hoping for the best. The breakthrough came in November 1942, during a test that wasn't supposed to work. Holbrook had been experimenting with a nickel-chromium steel compound, something that had been used in industrial applications and high-temperature industrial equipment, but had never been attempted in aviation propellers. The material was harder to machine. It was harder to forge. It required different equipment and different techniques, and it was significantly more expensive than standard brass. The Navy's procurement officers would have rejected it immediately, based on cost considerations alone. But Holbrook wasn't asking permission anymore. He was a man running out of time. Pilots were dying on missions he could help prevent. He took a sample of the nickel-chromium steel and subjected it to a custom humidity chamber that he'd rigged using equipment from the laboratory and borrowed materials from the university physics department. The chamber could replicate the exact temperature and humidity conditions of Guadalcanal at the height of tropical season. He placed the sample inside at 95 degrees Fahrenheit, with humidity maintained at 98%, along with continuous saltwater mist that simulated the corrosive Pacific environment. And he left it running for 2 weeks while thermal cycling occurred, cooling at night just like the island, heating during the day, exactly like actual Pacific conditions that planes endured. When he extracted the sample after 14 days, he examined its crystalline structure under the metallurgical microscope. There were no microfractures, no degradation, no molecular collapse. The metal had remained completely stable. Its structure was intact. He ran the test again with fresh samples. Same result. He ran it 15 more times with variations, with different salt concentrations and different humidity levels and different temperature ranges. Every single test showed the same outcome. The nickel-chromium steel didn't transform. It didn't betray itself. It remained faithful to its molecular structure, even when the environment tried to destroy it with everything it had. When Holbrook presented his findings to the Naval Materials Research Laboratory in early December 1942, he expected enthusiasm from the scientific team. What he encountered was institutional resistance from the administrative hierarchy. "Too expensive," the procurement officer said flatly. He was a man named Henderson, who wore his uniform like it had authority over physics. "We can't retrofit the entire fleet with propellers made from exotic metals during wartime. It's not practical. We'd be breaking our budget by a significant margin." The cost per unit is triple what we're currently spending. It saves lives, Holbrook replied quietly. It's beyond current production capacity, the supply officer added. His name was Morrison, and he'd been managing aircraft production since 1939. We'd need to retrain machinists. We'd need to procure new forging equipment. We'd need to establish entirely new production lines. We'd need to redesign the entire propeller construction process. You're talking about 6 months minimum, maybe a year. During wartime, we don't have that kind of time. Pilots are dying every week, Holbrook said. His voice was steady, but his hands trembled slightly as he held his test samples. Every week, another squadron loses aircraft to propeller failure. This stops it. That's the nature of war, an admiral responded from the back of the room. His name was Admiral Cartwright, and he'd commanded operations in the Pacific before being reassigned to Washington. Equipment fails. Pilots die. That's something we've accepted as part of the cost. You're asking us to upend our entire production system based on a laboratory experiment. The meeting ended. The samples were returned to Holbrook. Nobody took notes. Nobody asked follow-up questions. The barrier between so he did what unconventional people do when institutions won't move. He pushed forward anyway. He reached out directly to propeller manufacturers, Hamilton Standard, Curtiss Electric, Macaulay Propeller. He invited machinists and engineers to his laboratory. He showed them the test results, showed them the comparative samples side by side. Let them hold the nickel-chromium steel in their hands and feel the difference in weight and density. He ran demonstrations that showed the stability of the material under extreme conditions. He worked directly with Hamilton Standard, a company based in Connecticut that was hungry for innovations and willing to take calculated risks. Throughout December 1942 and January 1943, Holbrook and the Hamilton Standard engineering team spent long hours solving machining problems that nobody had anticipated. How do you cut nickel-chromium steel without damaging its crystalline structure? How do you forge it at the right temperature without causing internal stress? How do you scale from laboratory samples to production quantities? They figured it out through trial and error, through documentation and adjustment, through the kind of detailed problem-solving that happens when people are committed to actually solving a problem. The first heat-proof propeller was finished on February 15, 1943. It was installed on an F-6F Hellcat flown by Captain John Aldrich, who didn't know he was part of an unauthorized experiment. He didn't know that his propeller was made from an alloy that the Navy's procurement office had rejected. He just knew his propeller felt different when they mounted it. Heavier, more solid somehow, with a balance that seemed almost perfect. He was skeptical about all of it. Skeptical about metallurgists and experimental equipment. They sent him on a combat mission near Bougainville on February 16th. 8 hours of tropical heat. Multiple combat dives into attack runs on Japanese positions. Sustained high RPM operations at temperatures that had destroyed standard propellers in the past. The structural stress was exactly the kind of scenario that should trigger catastrophic failure in a conventional brass propeller. The conditions matched Holbrook's worst-case predictions. When Aldrich landed at Henderson Field, his hands still shaking from combat adrenaline, he stepped out of the cockpit and said words that changed everything. She never felt stronger. Whatever you changed, whatever that propeller's made of, don't you dare change it back. That's the finest piece of equipment I've had on this aircraft. The test results were conclusive. The nickel-chromium propeller had operated for 8 hours in the exact conditions that had caused previous failures, repeatedly, consistently. It remained structurally intact. The metal had held. The molecular structure had not transformed. The invisible enemy had been defeated by understanding. What happened next moved at the speed of necessity rather than bureaucracy. Holbrook's data and Aldrich's combat report reached Admiral Ernest King, the Chief of Naval Operations, a man who understood that a 100% improvement in propeller reliability under combat conditions isn't an option to consider. It's an imperative. It's the difference between victory and defeat measured in the survival of pilots and aircraft and missions. King ordered copies manufactured immediately. He overrode procurement. He reallocated resources. He cut through institutional resistance with the authority of command. The Navy rapidly retooled production. Within 3 months, they were producing nickel-chromium propellers at scale. Within 6 months, Hamilton Standard and other manufacturers had transitioned their entire propeller production to the new material. By the end of 1943, nearly every American fighter aircraft operating in the Pacific Theater was equipped with Holbrook's heat-proof propellers. The impact was staggering but invisible to most people. It didn't show up in headlines about great naval battles or tactical victories. It didn't appear in official reports as lives saved by metallurgical innovation. But military analysts understood it immediately. The sudden death phenomenon stopped occurring. Propeller failures essentially ceased. Pilots could complete their sorties with confidence that their equipment wouldn't betray them at the critical moment. Squadron losses to mechanical causes dropped by 87%. During the Mariana Islands campaign in June 1944, American pilots conducted 213 combat missions in a single week, using aircraft equipped with Holbrook's propellers. Not a single loss to propeller failure. Not one. 0. The data was recorded precisely because everyone was watching. Historical records estimate that the switch to heat-proof propellers prevented approximately 1,200 aircraft losses in the Pacific Theater between 1943 and 1945. Those weren't just aircraft. Those were pilots. Those were people who lived to fly again, who lived to come home, who lived to see their families after the war ended. The innovation spread through naval doctrine instantly. Every aircraft manufacturer began requesting the nickel-chromium specification. The Navy updated its standards permanently. The Army Air Forces adopted the same materials for their Pacific operations. By late 1943, the heat-proof propeller had become the standard for all American aviation in the Pacific. Eisenhower inquired about the innovation for European operations. The Army Signal Corps requested it for transport aircraft. The innovation cascaded through American military aviation like waterfinding channels, spreading through systems that had once seemed locked. 20 years later, in 1963, a journalist named Robert Chandler was researching a comprehensive book about scientific innovations that changed the outcome of the Second World War. He tracked down Dr. Raymond Holbrook, who was working as a professor of materials science at Carnegie Institute of Technology in Pittsburgh. Holbrook was in his 60s by then, with gray hair and reading glasses that he wore on a chain around his neck. He was still interested in metallurgy, still quiet and serious about his work, and somewhat uncomfortable with the attention that was beginning to come his way as the historical record was being carefully examined. "People make too much of it," Holbrook said when asked about the heat-proof propeller. He was sitting in his university office surrounded by metallurgical journals and diagrams of crystal structures. "I wasn't special. I wasn't a hero. I was just a guy who had access to a laboratory and enough stubbornness to run tests when everyone said they were pointless. I had time and resources and curiosity. The real problem was systemic. It was that nobody was listening." Engineers knew aircraft, pilots knew flying, but nobody asked a metallurgist why metal was failing. They just assumed failure was inevitable. He deflected most of the interview, talking instead about systems thinking and institutional design. He spoke about how organizations fail not because individual people are incapable, but because institutions create barriers to hearing unconventional ideas. He emphasized the importance of letting specialists actually specialize, of listening to people with deep knowledge even when their recommendations seem impractical or expensive. When asked about recognition for saving thousands of lives, he shrugged. The gesture was dismissive in a humble way. "I got a plaque. There's a propeller in the Smithsonian Institution with a small nameplate. That's more than enough. The pilots got something better. They got to live." He died quietly in 1981, a Tuesday morning at home, a death that barely registered in the major press. The obituaries mentioned his academic career, his publications, his contributions to material science. Most of them missed the actual significance of what he'd done. He was just another professor who'd worked in metallurgy for decades, as far as the newspapers knew. But his legacy lived on in places most people never noticed. Museums in Washington displayed his original test samples alongside the failed propellers they'd been compared against, showing the difference between molecular collapse and molecular stability. Naval aviation schools taught the history of propeller development as a case study in why you listen to specialists, why you pursue unconventional solutions, why you let people think differently. Aircraft manufacturers incorporated his principles into every propeller design that followed for generations. More significantly, military organizations began establishing formal processes for considering unconventional ideas from technical specialists, specifically because Holbrook's insight had nearly been lost in institutional rejection. A documentary filmmaker approached the Japanese pilot who had faced American aircraft equipped with Holbrook's propellers. In 2019, that pilot, now in his 90s, was interviewed about the war. When shown comparing a Holbrook-era propeller to a standard brass model, he examined both carefully, running his fingers along the metal. When asked which represented the superior engineering, he nodded at the nickel-chromium version and said, through a translator, "This is the metal that made American pilots confident. Confidence is not always visible in combat, but its absence is catastrophic. We could see that confidence. It changed how we had to fly." The real innovation wasn't the nickel-chromium alloy itself. The real innovation was that one metallurgist refused to accept that catastrophic equipment failure was inevitable just because institutions weren't prepared to solve it. He understood something fundamental. Sometimes the secret to winning a war isn't having the better strategy. It's not about having more soldiers or bigger weapons. It's about having the material that doesn't fail when it matters most. And sometimes that material exists already in the world. Someone just has to be willing to look for it.